Limits seem to show up in calculus all over the place. And if you've taken a rigorous course, you might have encountered the alien looking epsilon delta formalism. But why do these things show up? And why are we interested in them? So this video is going to be a heuristic one. We're not going to get into any details, but I want to try to motivate limits and show how they're not really the same thing as evaluating a function, though those things overlap not infrequently. Okay, so the problem you want to consider here is to consider a function f of x whose graph looks like, so let's draw a graph. Let's draw a plane, and maybe it looks a little bit linear, and I want to put a hole there, and let's make it curve up after. So this hole is at x equals 3, and the function value will put up at 4. Okay, so the first thing we can notice is that there's a big hole in the graph. And the question I want to consider is, what is the value of the hole? So, for example, if we wanted to fill the hole, then what value should we put it there? Okay, so after thinking about this, you can maybe see how evaluating the function at x equals 3 doesn't help. Because if we look at our graph, f of 3 is all the way up at 4. It's not even connected to the rest of the graph somehow. So that definitely isn't the same value as the whole. So evaluating f of 3 doesn't actually tell us anything. So let's reflect for a moment on what we should do here. It's not so obvious. Okay, so maybe you've had the idea now to evaluate f close to x equals 3, but not at 3. So say something like f of 2.9 is 1.99 and f of 3.1, sorry, is 2.3. So can we determine the value of the whole with this information? So one guess might be to say, okay, well, it looks like the values are going to 2, or maybe we should take an average. We should take halfway between 1.99 and 2.3. Okay, but if we think about the graph more, this last case is dubious because the graph curves up more after x equals 3, sorry. So this actually overestimates the value. So if we look past x equals 3, there's a steeper curve up. So the average value will be higher than the value of the whole there. So all we really know from the information of f of 2.9 and f of 3.1 is that the value of the whole should be between 1.99 and 2.3. That's not enough to pin it down. Okay, so maybe if we take a closer point that can tell us more. So let's say f of 2.99 is 2.05 and f of 3.01 is 2.14. So we're getting much closer now. So the value of the whole is probably not 2 anymore. We can eliminate that guess from before. But we have the same problem as we did above. We can't quite decide on a value between these two. We only know that the whole is somewhere between 2.14 and 2.05. So it seems like we're still stuck, but we're getting a little better. So think about how we can do this. So maybe you come across the curiosity, what if we could do this same process but infinitely? So if we could just keep getting closer and closer to 3. So let's see if we can write this down just for the sake of it. So for example, let's take a sequence f of 2.9, f of 2.99, f of 2.999, f of 2.9999, and keep going off to infinity. And let's say those values are 1.99, 2.05, 2.062, 2.0648, and we just keep going off to infinity. So the question is, what number should come at the end of this sequence? So we could complete this sequence, what number would we result in? Maybe it's 2.06 something, but we don't know the digits because it keeps changing. How do we do this? Well, this is the notion of the limit of this sequence. So we call this number that we get at the very end the limit of the sequence, if it exists. And some notation here, we often write, so in our problem, the value of the whole is, and the notation is this lim as x goes to 3 of f of x. So the limit as x goes to 3 of f of x. So a limit is like what we get if we completed an infinite process, in this case, in our problem, of getting x closer and closer to 3 without ever actually reaching 3. So what value would f of x reach if we could complete that? So this problem shows up all over the place in calculus, but as a teaser, you might know the definition of derivative, that the derivative at x equals c of f is defined as the limit as x goes to c of f of x minus f of c over x minus c. And if you look at this quotient here, that's exactly a hold function. So it's a function with a hole in it. And we can see that because if we were to try to plug in x equals c here, we would get f of c minus f of c over c minus c, which is 0 over 0. And that's nonsense. We can't make sense of that. So we really do need the limit to say something interesting there. And derivatives are incredibly useful. They're used absolutely everywhere to model the idea of change with respect to time or with respect to some other variable. So limits unlock a whole new language. And we didn't get into the details of how to calculate limits, but we need a formal definition and properties to help us calculate limits so that we can actually work with them.